Welcome to my Zoom session. This is what I'm planning on going over, y'all. I'm planning on going over differentiating between independent and dependent, differentiating between mutually exclusive and inclusive. I'm going to go over some of the stuff from 11.4 and 11.5, conditional probability. And then I'm going to also go over Venn diagrams again, because it seems to be a sticking point for people. So if you guys have questions for me in the midst of this, you need to go ahead and ask them of me, okay? Because that is what's going to enable you guys to get clarification as you move forward and be prepared for the test, which is next Wednesday, okay? All right, so I'm gonna go ahead and go into this. First talking about what is independent and dependent, okay? So that's what this slide is about. It says a grab bag contains 7 football cards and 3 basketball cards. An experiment consists of taking one card out of the bag and then selecting another card. What is the probability of selecting a football card and then a basketball card? So here's my question for y'all. And I want y'all to unclick your mics here and answer some of these questions for me. So if the first card is not replaced, so in other words, I took it out, I kept it out. That's what that means, right? Is that going to be independent or dependent? Someone answer me.
Dependent.
Sorry, say it again.
Dependent.
Why is it going to be dependent?
Because it's not replaced, so like it affects the cards.
Exactly. So how many cards did we start out with, y'all? Everybody type for me. Type for me in the chat. How many cards did we start out with? Go ahead and type in the chat, y'all. Tell me how many cards we started with. I see 10. Is that how many the rest of y'all think too? Come on, guys. I need you to engage here, because otherwise this is not going to do you any good anyway, okay? So yes, there's 10. Why? Because 7 plus 3 is 10, right? So that's how many cards we started with. Yes? Okay. So it says, what's the probability that the first one's not replaced? So we're going to talk about, that's going to be a dependent probability, right? When we pull a football card, actually that should say basketball right there. Yeah, I don't know what happened. We should say football and basketball. My bad. This one should also say football and basketball. But we're not going to worry about that right now. We're going to just talk through the problem. So this one's dependent, and it's dependent because we did not put the card back. Now, if we put the card back, it would have been independent, right? So we've got 7 of the cards that are football cards, right? And then we kept that card. So how many cards are left if we started with 10 and I kept 1 card, y'all? Go ahead and type me in the chat. Type me in the, there you go, 9, okay? So, so that means this number down here changed. Y'all see that? It changed from 10 to 9 because we kept the card. But we still have the same number of basketball cards, don't we? So, and remember, we're multiplying here because this is an and statement. Y'all see that and word right there? Sometimes the and word won't be there, and you guys are going to have to be able to still determine that it's an and statement. If it's or, the word will always be there, okay? Sometimes the and word is not going to be there. So here, what do? How do we do this type of problem? Anybody remember?
You multiply.
What do we multiply?
The top and the bottom.
There you go. We multiply across the top, so we're going to do 7 times 3, right? And 10 times 9. So that's going to give us 21 over 90, which reduces, remember, on y'all's quizzes and tests, y'all are going to always have to give me a reduced answer. So that's going to be 7 over 30, and if I divide 7 by 30, I get 0.23333. And if I multiply that by 100, which is what we would do by moving the decimal place 2 places to the right, that's going to be 23.33. Now this one over here, part B, says the first card is replaced. So this one's going to be independent, right? So again, it's going to be football and basketball. Just ignore that word right there, y'all, because it says selecting a football card and then a basketball card. So what's the probability that I pull a football card? Somebody tell me. What number over what number? Just put a number, a slash, and then a number for me. Go ahead and do it in the chat. 7 over 10, right, okay. Then we're going to multiply that. Remember, we're multiplying because that's an and symbol there, right? How many basketball cards do I have and how many total cards do I have when I'm talking about the number I'm going to multiply it by? So once again, show me in the chat, y'all, what number over what number am I going to multiply by? Yep, I see someone said 3 over 10. So again, so what are we going to do? We're going to multiply the 7 over 10 times the 3 over 10, right? Multiplying across the top, multiplying across the bottom. That's going to give us 21 over 100, isn't it, y'all? And that one can't, that one also can be reduced, right? To 7 over, whoa. But that's not right, y'all. That can't be reduced. I don't know what happened here. So see what happens when you try to create PowerPoints fast? Anyway, this should just stay 21 over 100. That right there is wrong. Y'all got me? I guess I just copied and pasted from there. But so it's 0.21, which is 21%. So does everybody understand the difference between independent and dependent? If you have a question, ask it of me now. Either unmute your mic and ask me, which would be beneficial to everyone, or type it in the chat. Does anybody have a question about dependent and independent?
What if it doesn't say if it's replaced or not replaced?
Well, I mean, you're going to look for words like I kept it, I returned it, I replaced it, I ate it. So if I told you I ate it, is it going to be returned?
No.
Okay, do y'all understand? So that's what you're looking for, words that kind of tell you, did it get put back in the group or did it somehow not go back in the group? That's what you're really looking for. Okay, does that help?
Yes.
Okay, so now we're going to talk about mutually exclusive and inclusive, okay? Those are the ones that people seem to be having more difficulty with than the dependent and independent. Now listen, dependent and independent have to do with and statements. Mutually exclusive and inclusive have to do with or statements. Those are things you got to keep straight in your mind, y'all, okay? They're totally different things. And statements when we multiply, right? Or statements when we add and subtract the overlap, okay? So this says there are 5 nickels, 3 dimes, and 5 quarters in your pocket. You randomly pick a coin. Find the probability of nickel. What does that symbol right there mean, y'all? Go ahead and type it for me. What does it mean? Everybody type for me. What does this symbol mean? Does it mean and or? I come on, only got one person responding. You guys should all be typing. See, this is how you engage and make sure you understand, okay? So if y'all aren't responding to me, then I'm not sure you understand. Follow? Okay, so what we want to do is we want to find the probability of a nickel or a dime. So here's my first question for y'all. What do we do first in a problem like this? Anybody can respond to me. You can type or you can say.
You add the total.
Yeah, so we have 5 nickels, 3 dimes, and 5 quarters, right? So what is 5 plus 5, y'all?
10.
Plus another 3?
13.
So we have a total of 13 coins. That's always going to be our denominator. Y'all with me here now? Okay, so when we talk about this one, this is going to be mutually exclusive. It says nickels or dime, right? Nickel or dime. You randomly pick a coin, one coin, y'all, not multiple coins. Now, if we were talking about picking more than one coin, then this would probably be an inclusive. Y'all follow me? But it says only one coin. So I reach into my pocket, I pull out one coin. What's the probability that I get a nickel or a dime? Okay, so what's the probability that I get a nickel? How many nickels are there, y'all? Type for me. How many total coins are there? So I see people saying there's 5 nickels. How many total coins are there? 13, right. So what are we going to do? First step here, we're going to do 5 over 13, right? Then how many dimes were there, y'all? Go ahead and type again, 3, right? How many total coins were there? 13, right? So now this time, there's no overlap between a nickel and a dime, right? They're 2 unique coins, yes? So we're going to do the 5 over 13 plus the 3 over 13, and this is going to be a mutually exclusive event. And anytime you pull one thing, y'all, or there's not something that's got some sort of commonality between it, that's when we know that this is going to be a mutually exclusive event. And again, mutually exclusive only has to do with or statements. And I don't know if y'all have noticed or if you've looked at your formula sheets, but there are formulas on there for and or statements, okay? So we add across the top and we keep the common denominator. Does everybody remember how to do the math here?
Yes.
Okay, all right. So now we're going to talk about an inclusive event, okay? So this one says a bag contains 6 yellow jerseys numbered 1 to 6. The bag also contains 6 purple jerseys numbered 1 to 6. You randomly pick a jersey, find the probability of yellow or odd, okay? So this is how I'd like to do problems like this. I literally would write out, I got 1 through 6 in yellow here, and I got 1 through 6 in purple. Y'all see that? And for some of you, it's going to help you to do this. Write it out, okay, so that you can see what it's talking about. Then it asked me again, so let me ask y'all a question. How many total jerseys do we have?
12.
12, right? So we're going to add the 6 plus the 6, right, guys? Okay, then it says, and how many of those 12 jerseys are yellow, y'all? Because that's going to be our first number. We're going to put
6.
that on. So we're going to do the 6 of these over the 12, right? Now, how many of them are odd numbers? What are the odd numbers, y'all? Go ahead and list them for me.
1, 3, and 5.
But we got 1, 3, and 5 over here too, don't we, y'all? So
Yes.
we got to go 1, 3, 5, 1, 3, 5. Y'all see that? Now I got a question for you. Do you guys see any numbers that fulfill both? They're both yellow and both odd.
Yes.
Which ones are both yellow and both odd, y'all?
1, 3, and 5.
The yellow one, the yellow 3, the yellow 5. Y'all got me? That's the really key. So this is an inclusive event because we've got some overlap over here, don't we, y'all? So what we're going to do then is we're going to take this 6 of these yellows and put them over 12. We're going to take the 1, 2, 3, 4, 5, 6 of the odd numbers and put them over 12. And then the ones that were represented twice. See, we represented these 1, 3, and 5 over here in the yellow, and we also represented them in the odds. Y'all notice that? So we have them overrepresented right now. So we have to subtract 3 of the 6 that we overrepresented. So then we're going to do 6 plus 6, which is 12, minus 3, which is 9. That's 9 over 12, which would be 3 over 4, right? And that's 75%. I think most of y'all know that, yes?
Yes.
Matthew said, what problems do you recommend to use a table? I'm going to get to those, Matthew, okay? So give me a minute and I'll get to some of those as well, okay? All right, so this one right here, this might answer your question, Matthew. So this actually was given to you as a table, and this is from the review for the test, y'all. It says the table shows a distribution of male and female left and right hand students in the math club. Make a table that's joint and marginal relative frequencies. So when it comes to making tables, I usually do those when they're asking me for conditional probability. I don't usually make a table if I don't need it from a conditional probability standpoint. And what do I mean by that? Let's talk about, let me go ahead and talk y'all through this question and I'll explain to you what I mean by conditional probability. So first of all, what I would do is I would expand over here for some totals and I would expand down here for some totals, okay? So I would find the total number of people that were in this whole table here. So I added all these 4 numbers together and I got 79, okay? I think all of y'all can do that. Then I'm going to create another table. And what did I do? All I did here was I expanded down here and I expanded over here so I can have totals, okay? So what we're going to do now is we're going to take this 2 and we're going to put it over the 79, and that's what's going to go in this box right here. Y'all see that? So, and remember, when our totals, when we add them together, they're always going to equal 1. So let's talk about how we do that. So we're going to go 2 over 79, that's 0.025, and I'm just going to keep working this table and then y'all see what we're going to do with it. Then I'm going to do right-handed, and that's 35 again over the 79. That's 0.443. Then I'm going to do the 6 over the 79. That's 0.76. And then I'm going to do the 36 over the 79, okay? So now I'm going to add these 2 numbers together and get what goes here. I'm going to add these 2 numbers together and get what goes here. And so I'm going to work that all the way through, okay? So I'm going to add 0.025 to 0.443. That gives me 0.468, sorry. I'm going to add 0.076 to 0.456. And that's going to give me 0.532. Now, here's the thing. If when I add these 2 numbers right here together, y'all, they don't equal 1, then I've made a mathematical error somewhere. So I need to go back and check, okay? Now I'm going to add the columns. So I'm going to add the 0.025 to the 0.076. That gives me 0.101. I'm going to add these 2 numbers together. That gives me 0.899. When I add these 2 numbers together, I'm going to get 1. So now comes your question, Matthew. When would I use a table? I'm going to talk about it here. It says given. Do y'all notice this word given here? Really important. Given that a person is left-handed, what is the probability that they are female? Okay. So I want y'all to watch what I'm about to do. So if it's talking about left-handed people, right? Aren't we talking about this column of information here? Can y'all see that?
Yes.
Okay. So then all we have to do is take this total, and how many of those left-handed people were female, y'all?
0.076.
Yeah, so we're going to put that 0.076 over that 0.101. Did y'all see that? 0.076 divided by 0.101 equals 0.752, which is 75.2%. Okay, now let's talk about this other one. Given that a person is male, what is the probability that they are right-handed? Okay, so are we going to talk about a column or a row here, y'all? Type it in for me. Are we talking about a column or row here of people that are males? Come on, guys, type for me. Row, row. I'm hearing rows. So rows are horizontal. Y'all got that? Columns are vertical? Just in case you didn't remember that. Yeah, and you guys are right. It is a row, right? So what row is it? It's that row right there. Do y'all see that yellow row? So we're talking about all males. So what's the total number of males we have? Y'all can type it for me or talk, one of the two. Isn't it right here? 0.468, okay? And what is, now someone said 37, and that's true too. We could take the 37. So what this person, Carly, said, 37. So Carly said 37 because she added the 2 to the 35, right? That is 37. And then she's going to put what number over that 37, y'all? What number?
79.
No, because we're talking about just males. So the total number of males out here would have been 37. If we were to add 2 to 35, isn't that 37, y'all?
Yes.
How many of those males, though, were right-handed?
35.
35. So to get the answer for this second part, you could take 35 over 37. Do y'all see that?
Mm-hmm.
So I did it with the percentages, but you could just take the total. So you could put the total of 35 here, and 37 right here, and that would have been 35 over 37. Y'all got me? It would have got me the same answer no matter which way I do it. And if it works better for y'all to just do it with the straight up numbers, in other words, let me show you what I mean. So for 2 plus 35, that's 37, right? 6 plus 36, that's 42, right? 2 plus 6, that's 8. 35 plus 36 is, what is that, 71, y'all? Yeah. So remember, you can always take these totals down here and divide or put the number over top of them. So you could do it with just numbers too, okay? And it doesn't matter to me which way y'all do it. You can do it with the table by putting your total numbers here, or you can do it the way I did it. It doesn't matter, okay?
So I did it on Delta Math.
Right. So it doesn't, whichever you're more comfortable with and whichever one works better for you guys, that's the way I would do it. Any questions on that one?
No.
Anybody? No? Yes? Okay. I got one more thing I want to go over with you. I want to go over this Venn diagram with you guys, okay? So a group of 44 students who are animal lovers were surveyed to determine which of 3 types of animals they own. The Venn diagram has the results of the survey. So using the Venn diagram, find the probability of the problems, and our problems are going to be over here on the right. So I got a question for y'all. How many total students were surveyed? Anybody? I heard someone say it. 44, right? Okay. How would we find out if somebody didn't have an animal? Does anybody know how we could find out if anybody that was surveyed didn't have an animal?
You add the ones in the Venn diagram and you subtract it by 44.
You got it. So if we add up all these numbers, y'all, I did it beforehand. If I add 10 to 10, that's 20, right? 6 plus 2 plus 2 is another 20. So that's 30. And 9 plus 1 is another 10. Sorry, I should have said 10 here. 10 plus 10 plus 10 plus 10. So that's 40, right, y'all? How many people didn't have an animal at all that were surveyed?
4.
4, exactly. So, but remember, it's our total number up here that we're always going to use for our denominator, okay? That's really important. So on this problem, it says, in OR problems, you can add all the numbers that are in both circles and put that number in the numerator and the total in the denominator, right? Okay, so let's look at this first question. It says, find the probability that you have a cat or a bird, okay? So let's figure out how many cats we have, y'all. How many cats are there in this drawing? Can anybody tell me? Go ahead and type it in the chat. How many cats are there in that circle right there, y'all? Anybody? 10 plus 10 is what, y'all? 20 plus another. Yeah, I saw someone write. So 10 plus 10 plus 6 plus 2, that's 28, right? Okay, now wait a minute. When I'm going to show you all the easy way to do this problem, okay? So the easy way to do this problem, when we're talking about OR problems, is just to add everything that's in both circles, okay? So this one said cat or bird, right? So we're talking this circle and this circle. So cat and bird. So we got 10 plus 6 plus 2 plus 10 plus 1 plus 2. Did y'all see how I did that? 10 plus 10, I did the 10 plus 10 right there, plus the 6 plus the 2, plus the 2, and I don't know what happened to my 1, it disappeared. So that would have been, yeah, that's 31. So somehow my 1 disappeared from there, but that's okay, y'all. So we're going to add for all of these numbers in these two circles together, and then we're just putting them over the 44. So when it's an OR problem, that's all you have to do, okay? So let's talk about the next one. I think it's cats or dogs. So we're talking about this circle and this circle. Let's see if y'all can give me the answer for this one. Tell me how many cats, how many are in this circle and this circle total? Add all those numbers together and tell me what you get, y'all. Cats and dogs. I think Z already gave it to me, didn't you?
Is it 39?
So we got 10 plus 10, that's 20. Plus another, what, 30? Yep, it's 39, isn't it? Y'all see that?
Yeah.
There are 39. So what number are we going to put that 39 over, y'all, when we're looking for this OR statement of cats or dogs?
39.
What number are we putting 39 over? I said.
Oh.
What's our denominator, y'all?
44.
Yeah, that's it. So we're going to add up all those numbers and put them over 44. So that's 39 over 44. That's 0.8864, which is 88.64%. Okay, let's do this last one, which I think was what, dogs and birds? Dogs or birds? So go ahead and tell me, how many dogs or birds are there, y'all? Count them up. Dogs or birds?
30.
30. And what are we going to put the 30 over, y'all?
44.
Exactly. So we're going to put that 30, add them all together. We get 30 over 44. And that's supposed to be 15 over 22, y'all. My slash disappeared when I imported this. So much for doing things correctly. And so that 15 divided by 22 is 0.6818, which is 68.18%. Okay? Now we're going to talk about and statements, okay? In and problems, you find the overlapping number by adding them together, and then you put that number in the numerator and the total in the denominator. So let's go back up here, and we're going to say cats and birds now. So cats and birds. So what's the overlap between the cats and the birds, y'all? What two numbers are y'all going to add together for the overlap of cats and birds?
10 and 2.
Yeah. So that's all you have to do for these problems, y'all. They're easy. Add the 10 to the 2 and put it over what number? What's our total?
44.
There you go. So you're going to put 10 plus 2, that's 12 over 44, right? 12 divided by 44 reduces to be 3 over 11, and that's 0.2727, which is 27.27%. Got it? Okay, again, let's talk about this next statement, cats. Now we're going to make this one cats and dogs. So again, tell me, what is the overlap, y'all, between the cats and the dogs? What are the two numbers we're going to add together there?
6 and 2.
Yes. So what's 6 plus 2, y'all?
8.
So we're going to put the 8 over the 44, right? Y'all tracking with me here? Making sense?
Yes.
So this is going to be, again, we can reduce that to be 2 over 11. That's 0.1818, which is 18.18%. Okay? Got one left, right? The dog and the bird. So we're talking about dog and bird here, these two. What's the overlap there, y'all? What two numbers are we adding together this time?
2 and 2.
So we add the 2 plus the 2. That's 4 over 44, which, again, there should be a slash right there, y'all. I don't know what happened to my slashes or my division signs, whichever you want to say it. So it's 1 divided by 11, which would be 0.0909, which is 9.09%. Is this helping, y'all?
Yes.
Yes.
Okay, so if you have, what other questions do y'all have? Because I can answer any other questions you have. So are there other things that you guys are still confused about?
So, like, on the quiz, there was, like, a question, it was like the probability of A equals like a number, and then probability of B equals something else. And then it was trying to like the number that does not do anything.
Okay, let me go to, I've got a PowerPoint on that I did when I taught it. And you might want to go back and look at, I'm trying to think when I did that one. There's the one on 11.2, 11.3, the Delta Math assignment. That's the one you're talking about, right? The second Delta Math assignment. Is that the one you're referring to?
Yeah.
Oh, yeah.
Yeah, so when, let me go ahead and see if I can open this up.
How come 11.1 wasn't on the quiz?
It was on the quiz.
Was?
Yeah, it was. It's just that 11.1 is so simple that you guys probably just even overlook it, honestly. 11.1 was, I mean, compared to when you're dealing with, I'm trying to find, where's that slideshow, y'all? When you're trying to compare it to independent, dependent, exclusive, and mutually exclusive and inclusive, it's like really simplistic. And you guys have been dealing with that kind of stuff since you were little. Follow me? Because y'all been learning about probability for years, right?
Yes.
So all I'm saying is you're looking at those things and going, yeah, I don't know if I get this or not, but for reality is you probably do, because it's that easy. That stuff from 11.1, I mean, most of y'all, if you went back and did the 11.1 homework now, you wouldn't have any problems with it at all, because it's so simplistic in relationship to independent, dependent, and mutually exclusive and inclusive. Do you understand?
Yes.
It's so simplistic that you guys would be like, oh, okay, I got no problems with that. Okay, so I'm going to put this up here, and hopefully this will help y'all. This was, I didn't need to go all the way back to the beginning, but these are just some of the problems from that 11. So this is the kind of stuff you're talking about?
Yes, ma'am.
Okay. So it says, given that the probability of A is 0.75 and the probability of B is 0.62 and the probability of A given B. Now, we've been over this now. So even when y'all did this, we'd already been over it, but you might not have understood it as well as maybe you do now. This is an and statement, right? So what operation do we do when we have and statements, y'all?
Multiplication.
Multiplication, right? So we're going to take the probability of A and multiply it times the probability of B, given that B has occurred. But so wait, it says find the value of the probability of A and B, given that B has occurred. So what does that mean? So the probability of A given B that has occurred, we take the probability of A and B. So y'all remember, I think it was in 11.4. Y'all with me here? When we did 11.4, I just make this very simplistic with my kids. I tell them, put the two things, you know, the and statement on top and put whatever's by itself on the bottom. Now, what is by itself? It's this part right here. Y'all see the B? So all we have to do here is take this probability right here and divide it by B. Y'all follow what I'm saying? That's all we have to do to find out the probability of A. And why is that? Because the probability of A and B is the probability of A times B, isn't it, y'all?
Yes.
Okay. So if what I want to find out was A, don't I just divide it by B? That's what I do. Y'all understand? So that's what we're going to do. So we're going to actually take the probability of A given B. We're given that right there. Y'all see that? We're putting it over here. We're looking for the probability of A and B. That's in our numerator always, y'all. Anytime if it's written out in words, whatever it says, like if it's dogs and cats, or it's pigs and mice, or it's corn and potatoes, y'all follow me? Whatever that and statement is, it always goes in the numerator. Got me? And
Yes.
then you put the individual probability in the denominator, whatever it is, okay? So how do we do a problem like this? We multiply both sides by 0.62, right? And that's going to cancel it out from over here, isn't it, y'all?
Yes.
Okay, so that just leaves us 0.62 times 0.95, which is the probability of A and B. So this is just algebra, right? Once we set the problem up, y'all see up here, once we set the problem up, then we're just doing algebra. That's it, okay? Let's look at another one, okay? This one says, given that the probability of A is 0.5 and the probability of B is 0.26, and the probability of A and B is 0.22, find the value of the probability of A or B, rounding to the nearest hundredth. thousandth, sorry. So on this one, this is what kind of a statement? An and or an or statement, y'all?
Add.
Look, what does it say right here?
Or
Or. So we're going to add the individual probabilities together, and then we're going to subtract the overlap. You guys have got to get in your head that that and statement is the overlap, okay? That's what it is. Got it? So all we have to do here is add A plus B and subtract A and B. That's all we have to do to find the probability of A or B, okay? So I wrote this as a or statement. Probability of A plus the probability of B minus the overlap. That's what A and B are, okay? So this is, again, just a simple, I would call almost an elementary school math problem once you guys put the values in, right? Okay, so that's all we have to do for that one. Now, this next one, given that the events A and B are independent. Now, what does independent mean? That means that what happened first didn't affect what happened second, okay? So that means anytime they're independent, all we have to do is multiply the probability of A times the probability of B, okay? To get the probability of A and B, okay? That's the key here. We're not changing any numbers. So the probability of A and B, and that and symbol right there relates to that word, right? So we're going to take the probability of A here, put it in there. We're going to take, we don't have the probability of B, do we, y'all? We're going to solve for that. We would just leave that probability of B there, and then the probability of A and B here, we're going to put it right there. Do y'all understand?
Yes.
Okay, so then what did I do again? Now we're just doing an algebra problem again, aren't we?
Yes.
So how do we get rid of the 0.89 here, y'all?
You divide.
Exactly. So that's all it is. So if you can set these up, now again, the key to this problem is that word independent right there. Y'all see that? When it says independent, all I have to do is multiply probability of A times the probability of B to get the probability of A and B, okay? And here's our last one. I think this was the last one that I did. Given that events A and B are independent again, with the probability of A being 0.9 and the probability of B given A has occurred is 0.76, determine the value of the probability of B, okay? So let's talk about how we set this one up. It says when the events A and B are independent, aren't we just multiplying them then? Right, y'all? We're gonna multiply A times B, that's what we said. That's gonna give us the probability of A and B, okay? So this is the probability of B given A has occurred. It's just probability of B. Why? Because this is going to be the probability of A and B, probability of A and B divided by the probability of A. If this is the probability of A and B, isn't that the probability of A times the probability of B, y'all? Like this, see probability of A times probability of B? What happens when I have a probability of A on top and a probability of A on the bottom? If this was a 3 and a 3, y'all, what would they do to each other? If I have a 3 in the numerator and a 3 in the denominator, what do they do to each other, y'all?
turn into 1.
They cancel each other out, don't they?
Yes.
So that
Oh,
means
yeah.
what am I going to be left with? All I'm going to be left with is the probability of B. So what does that really mean? It means if A happens, and I want to know the probability of B that given that A happens. So let's just say, what's the probability that I am going to drive my car today and go to the store? So the probability is given that I drive my car, I'm going to go to the store. Y'all got me? So I drove my car today. So what do you know happened?
You went to the store.
Exactly. That's all that is, y'all. That's really what it is. Y'all follow? If you're given a portion of it and you know that one thing happened, then you know that the first thing had to have occurred. Got it? So the probabilities of A cancel each other out. So the probability of B would just be that 0.76 right there.